Okay, section 13.4 is on the colligative properties of non-electrolytes. And so I'll write that down, colligative. Perhaps a new word for you. When you dissolve something into a solvent, that's going to change perhaps the chemical properties, like new chemical reactions are possible for the solution. But colligative properties are a little bit different. They're usually changes to the physical properties of the substance, of the solution. And what's really cool about them is that they don't depend on the chemical identity of the solute. They depend only on the concentration. So it doesn't matter if I have water and I dissolve salt or sugar or any other substance, the colligative properties will respond in kind of the same way independent of the chemical identity of my solute, which is pretty crazy. So the colligative properties we're going to go over are vapor pressure lowering, freezing point depression, boiling point elevation, and osmotic pressure. So those four, we'll take them in turn. The first one is vapor pressure lowering. And to see why vapor pressure is lowered in a solution when there's a solute dissolved in it, we're going to turn to figure 13.10. So here we see on the left, if you have a volatile solvent, there's going to be some number of particles that are in the vapor phase at equilibrium. It'll have a vapor pressure. And that happens because some of the let's see if I can get my mouse to work. There we are. Because some of the solvent molecules that are on the surface are going to escape into the gas phase. Oh, I need to learn how to do this. I think it's just that my mouse like double clicks sometimes. I've got a bad mouse button or something. Okay, and some of the vapor molecules in turn are going to collide with the surface and stick, and those two processes will reach an equilibrium state. Well, on the right here we have a solution with some non-volatile solute in it, like maybe salt. Salt doesn't have a high vapor pressure. It's a solid at room temperature. And when you dissolve salt into water, it still doesn't have a vapor pressure. You don't have salt escaping into the atmosphere. However, it does occupy space. It is really there. And you'll notice in particular, there's no reason those salt solute particles shouldn't be occupying some of these positions on the surface. And so they're going to take up some of that surface space, making fewer solvent particles able to escape into the gas phase. If you have a swimming pool and you've ever had to maintain it, then you'll know that it actually makes a really big difference if you cover that pool with plastic versus leaving it open as far as how rapidly the water will evaporate away and need to be replenished, right? If you cover your swimming pool with plastic, then it's not going to evaporate away very quickly at all. If you leave it uncovered, then you lose a surprising amount of water to evaporation. I actually don't own a pool, but so I've been told. All right, so having a non-volatile solute is going to be like a partial covering of the water on the surface of your solution because they occupy some of those surface positions. So that is sort of a microscopic description of what happens. Oops. Sorry, we'll get to that in a moment. We can talk about vapor pressure lowering or vapor pressure depression in mathematical terms. So we have a formula that's called Raoult's law. So Raoult studied the vapor pressures of solutions carefully, and he found that the pressure of some volatile substance is going to equal the pressure of that substance when it is pure. And so that, oops, it's not a star, it's a not. I apologize. So this is the vapor pressure of the pure substance, if there's nothing dissolved in it. And we'll multiply that by the mole fraction of A. So if you've added some solutes, then you'll have a mole fraction of the solutes, and you'll also have a mole fraction of the solvent. So if 75% of the particles are solvent particles, then the observed pressure will end up being only 75% of the pure substance's vapor pressure. So a solution which follows Raoult's law is called an ideal solution. Just like our ideal gas law doesn't actually capture the true behavior of real gases perfectly, Raoult's law doesn't capture the vapor pressure behavior of gases perfectly, but it works well enough, and it works better for some substances than other substances. So what makes a good ideal solution? Which types of solutions follow most closely to Raoult's law? Well, those are the ones that have A-B interactions. That is, interactions between the solvent and the solute that are similar in strength to AA and BB interactions. Okay, so what this, you remember when we talked about solubility, the solute-solute interactions are going to be broken up when the solute dissolves. The solvent-solvent interactions are broken up when the solvent has to make room, make space for the solute particles, but they're replaced by A-B interactions. And so if these are too far out of balance, then the solubility is low, and the closer in strength they are to one another, then the higher the solubility tends to be. So a bit of a consequence of this is that the solutions which most closely follow Raoult's law tend to also be those solutions that have a high solubility for its solute. If you have we'll say non-ideal solutions. And every solution is non-ideal to some small extent, but when you have solutions that are particularly far from Raoult's law, well, they'll come in two varieties. There will be ones with particularly strong A-B interactions. Okay, so that means that the solvent-solute interactions are stronger than these solvent-solvent and solute-solute interactions. So interactions between the solute and the solvent are particularly strong. Well, that's going to have the pressure that we observe be actually lower than what Raoult's law would predict. So these will be solutions which have a particularly low vapor pressure, lower than Raoult's law would suggest. And then you can have some solutions with weaker A-B interactions. And this means weaker than the cohesive forces with the solute to solute and solvent to solvent. So if you have weaker A-B interactions, then the pressure that you observe will actually be greater than what Raoult's law predicts. And I think this makes a lot of intuitive sense. You mix your solvent and solute together to make a solution. Well, if they have strong attractive forces to one another, well then of course the solvent is going to be less likely to escape that solution, into the vapor phase because, well, now it wants to minimize its energy by staying close to solute particles where it can have these positive attractive forces. And if you have weak A-B interactions, then you've disrupted the solvent-solvent interactions, you've replaced them with something that's really weak, and that means that the solvent particles are being held less forcefully than before, and it's particularly easy for them to escape out into solution. So I think all of this makes intuitive sense, and we'll never deal with non-ideal solutions in a quantitative way beyond just making this observation, that some of them have higher vapor pressures than we expect, some of them have lower vapor pressures than we expect, and we can explain that in terms of their the strength of their interactions. Now, one last thing. I'll go ahead and erase the non-ideal solutions part here. If you have two components of a mixture that are both volatile, like say I mix water and ethanol, both of which have vapor pressures, then we can say that the total pressure is going to equal the pressure of A and the pressure of B. And so that is going to equal chi A P naught A plus chi B P naught B. Now, as a result of this, if you have a mixture of two volatile substances, they will have different pure substance vapor pressures, and they will have different mole fractions. And you can actually get a case where the composition of the vapor phase is different than the composition of the liquid phase. Say, let's consider water and ethanol. Now, ethanol has a higher vapor pressure than water. That means if you leave a glass of water and a glass of ethanol out, the ethanol will evaporate more rapidly. There will be more ethanol in the air than there is water. Ethanol has a higher vapor pressure. So let's suppose we get a mixture of 50% water to 50% ethanol. The composition of the liquid phase, the solution, is 50-50. But because of the higher vapor pressure of the ethanol, then the vapor phase is going to have a higher composition of the ethanol, right? If I change this to chi water, P naught water plus chi ethanol, P naught ethanol. Well, if it's a 50-50 mixture, then these will both be 0.5. But the higher vapor pressure for pure ethanol is going to make ultimately it a larger contributor to the total pressure. You'll have more ethanol in the vapor phase than liquid water. And anyway, we'll explore this in detail in our quiz for colligative properties. So I won't get into a practice problem about it right now, because we'll basically solve this exact sort of problem. Now, we know that the Dalton's law of partial pressure says that pressure of A is equal to chi A times P total. And so if we wanted to figure out the mole fraction of A in the gas phase, then we would figure out what is the observed vapor pressure based on the mole fraction in the liquid phase, and divide that by P total. So here we've got two different mole fractions. There's the liquid phase mole fraction, which is what goes into Raoult's law. and then the vapor phase mole fraction, which just sort of emphasizes how the vapor phase has different composition. We can calculate that composition itself based on Dalton's law of partial pressures. Okay, so let's leave vapor pressure lowering behind here and move on to our next colligative property. And that is freezing point depression and boiling point elevation. All right, so here we see a figure which demonstrates how freezing point depression works. On the top we see a pure liquid, and as the temperature gets low enough, then those particles will organize themselves into a solid. If you have a solution, though, your solvent particles have these solute particles interspersed among them, and that disrupts the formation of a solid lattice. You can see on the bottom right here, as you approach the freezing point, the solute particles are beginning to organize themselves into a solid lattice, but they're disrupted by the solute particles that are pushing them out of the way and taking up space. And the fact that they're being pushed out of the way means they're not able to form proper hydrogen bonds in the case of water, or just they aren't able to form whatever proper intermolecular forces the solute happens to exhibit. And so the consequence is that it isn't actually solid yet. You're going to have to lower the temperature even more in order to get the solution to actually freeze. Boiling point elevation is a little bit different in the microscopic perspective. The idea is that because you have depressed vapor pressure, then even at your normal boiling point, your vapor pressure will not equal 1 atmosphere, because the solute is taking up those surface positions and preventing some of your solvent from accessing the surface where it can vaporize. And so that vapor point depression, that vapor pressure lowering that we were just talking about has as a consequence that it will you'll need to heat your solution up to higher and higher temperatures in order to finally achieve boiling. And you may recall that boiling is the state where the vapor pressure is equal to the actual ambient atmospheric pressure. And so it seems like it's really similar, and in fact the equations that we'll show you in a moment are really similar, but vapor pressure lowering is the real cause for boiling point elevation. And this disruption of intermolecular forces by solute particles is the reason for freezing point depression. We can see here on figure 13.13 the consequence of adding a solute to a solvent. So here we see a phase diagram for the pure solvent. It would have a transition from the liquid to the solid phase right here at this freezing point temperature. I'll kind of extend this line down here. Right, and the normal boiling point would be right here, where at 1 atmosphere of pressure you transition from the liquid to the vapor phase. So this is what the phase diagram would look like for the pure solvent. Well, if you add a solute and it becomes a solution, well, the freezing point is going to be shifted over to the left to lower temperatures. So this is the new freezing point. That's the freezing point depression. And the vapor pressure lowering is going to lead to a new boiling point up at a higher temperature. So you'll have delta TF is the change in the freezing point temperature, and delta TB is the change in the boiling point temperature. Okay, so how can we actually calculate delta TF and delta TB? So freezing point depression says that the freezing point for the solution is going to equal the freezing point for the solvent, that is the pure solvent freezing point, minus Kf, oops, that should be lowercase m, Kfm. So this is the pure freezing point, and this is a constant called the freezing point depression constant. And each solvent will have its own value for the freezing point depression constant. And then this is the molality. And I'm going to put the total molality right here. You know, if you had a solution and you added lots of different solutes, well, they would all add up together. So this would be the total molality of all different types of solvated particles in solution. Now for this chapter, we're going to consider non-electrolytes. And for this course, we'll always sort of consider cases where there's only one chemical compound dissolved in solution. And so the molality for today is really straightforward. That's just the molality of your solute. And so we can also kind of often express this as delta TF is equal to negative KFM. So the change in the freezing point temperature is going to be your freezing point depression constant times the molality, and it's negative because the change is lowered, and freezing point depression constants are given as positive values. Okay, so what about boiling point? Well, the boiling temperature for the... Sorry, I need to concentrate on my writing. The boiling point temperature for the solution is going to equal the boiling point temperature for the solvent. That's the normal pure solvent boiling point temperature. This will be plus Kb times m. Again, that's the total molality. Pardon me. Kb is a boiling point elevation constant. And it is different than Kf. It's usually smaller. And each solvent is going to have its own value for the Kb. And here we can say delta Tb is equal to, this time it's a positive Kbm, because the boiling point will be elevated instead of depressed. And again, we're actually going to work some of these problems in the quiz. And so we'll go ahead and leave the problem solving to the quiz video, which I'll record in a few moments. Okay, so the next colligative property is osmotic pressure. Okay, so let me put up the next figure here. Oops, oh, sorry. Table 13.3 just gives you some values for freezing point depression constant, boiling point, and boiling point elevation constant for a number of different substances that may be useful to you in solving problems. Okay, so here's osmotic pressure. And it's a bit of a complicated idea here. So the idea is that solutions are going to exert sort of a pressure because of the amount of solute that is dissolved in them. And the best way to really understand this is to first talk about the idea of a semi-permeable membrane. A semi-permeable membrane is a barrier which has it has holes in it, has pores, and the size of those pores are just right to allow water to pass through, but not to allow solute particles to pass through. And so what you can do is put water in a chamber that is separated by a semi-permeable membrane, add solute to one side, and even if the water levels start at the same level, once you add the solute, water is going to flow from the pure water side into the solution side in order to sort of equalize. Hold on a second, let me explain this. It actually is just a matter of diffusion. If you look at the microscopic picture of that semi-permeable membrane, you'll realize that every time a particle encounters a pore on the left side, it's going to be a water particle and it'll be capable of moving over to the right. But half the time a particle encounters a pore from the right side, it'll be a solute particle. It can't pass through and it just bounces off. And so at the beginning there is going to be a net flow of water from the pure side to the solution side. And it's just a matter of like the probability that a water molecule is going to pass through a pore on the left versus the probability that a water molecule is going to pass through a pore on the right. There's nothing more fancy about it than that. Then as it goes on, water will flow from the pure side to the solution side, and you'll see the water levels eventually will no longer match one another. The solution side will have a column of water above the water level of the pure side. Above the level of the pure side. Okay, and the hydrostatic water pressure generated by that extra column of water is what we call osmotic pressure. Now eventually, because of this flow of water, you're going to have a higher pressure on the right side, and it will slightly dilute the solute particles on the right side. And eventually, these factors will lead to an equalization of the rates of water molecules passing from right to left or from left to right, and you'll reach a steady state. Okay, so maybe that was like an overly complex description of what osmotic pressure is. But we can talk about it in terms of a couple of practical examples. So reverse osmosis is a process for purifying water. What you'll do is take salt water, often from the ocean. Countries that live by the sea and don't have ready access to fresh water see all of the ocean before them and say, I wish I could drink that. And so they will construct these massive water purification plants that use reverse osmosis to purify the salt water. What they have is just a series of these semi-permeable membranes, and you need to apply a high pressure. If I can go back here, if I apply a pressure on the right side mechanically, then I can actually force the osmosis process to act in reverse. I can force my saltwater solution to pass through the membrane and produce pure water. Now that takes an incredible amount of mechanical pressure, but it can be done. And so this is reverse osmosis, and what you get out of it, the product, is pure water, which is obviously valuable to people that want to continue their lived existence on Earth. And so that's one example. And then another is has to do with medical solutions. Like if you've ever gotten an IV, sometimes there are medications in IVs. Sometimes they're just filled with water to hydrate you. But it's never pure water. It's always what we call an isotonic solution. And that is a solution that has some salt in it or electrolytes in it. And it's important that you get the concentration of electrolytes in your IV solution to match what is the natural electrolyte composition of your blood. And the reason is because our red blood cells, I'll draw one here. There's a nice happy red blood cell. All of our cellular membranes are selectively permeable membranes. They're able to pass water and at times some solutes, and in particular there are mechanisms for passing solutes when they need to, but water can always kind of flow in and out while solutes generally cannot. And so if we were to take a solution of pure water and put that into our blood, then the pure water would flow into the red blood cell until it expanded. I'm going to try and draw what it actually kind of looks like under a microscope. It becomes bloated and it expands. There's a high pressure of water inside it now, and eventually it ruptures. And that's obviously bad. We don't want our red blood cells to rupture. On the other hand, if you have a solution which is too salty, then the water is going to be leached out of the red blood cell, and it will become, oops, I should have grabbed my graphics tablet, because as problematic as it is a lot better at drawing than my trackpad here. That's okay. It will shrivel up. Here's a shriveled little red blood cell that has lost all of its water because it was given an environment that was too salty. And of course that's damaging to the red blood cell as well. So anyway, osmosis is extremely important when you're considering IV solutions that you might receive or give to a patient. Okay, let's get rid of that. All right, so how do we calculate osmotic pressure? This is a really remarkable equation to me. The way to calculate osmotic pressure, we'll use the Greek letter pi to represent osmotic pressure, and that is equal to nRT over V. This is obviously just a rearrangement of the ideal gas law. And the pressure of a gas is equal to the number of moles times the gas constant times the temperature divided by its volume in liters. Well, guess what? The osmotic pressure exhibited by a solution is equal to the number of moles of solute times the very same gas constant. So this would be 0.08206 liters atmospheres per mole Kelvin, times the temperature in Kelvin over the volume in liters. It's the very same equation. Only gases are really dilute compared to solutions. You'll get pressures of 1 atmosphere or 0.8 atmospheres if we're considering the atmospheric pressure at Cedar City. Typically in our problems involving gases, you have low pressures. Well, let's look at what happens with a solution. So let's calculate pi for a solution which contains 75 grams of sugar, C12H22O11, in 200.0 grams of water. Now, that would be a sweet water solution, but it's really not an absurd amount of sugar to put in water. You could easily measure that out, stir it up, and it would dissolve just fine. What would be the osmotic pressure? Well, we need to figure out how many moles of sugar we have, and what would be the volume of the water. Oh, and I need to give you a temperature. Let's just say at 25 degrees Celsius, at room temperature. Okay, so let me pull up my calculator here. Sorry, I am Googling the molar mass of sucrose here. C12H22O11. Okay, that's 342.3 grams per mole. So we have 75 grams of C12H22O11. No, I've forgotten it. 342.3 grams is 1 mole. So now we'll pull up my calculator. And we have 75 divided by 342.3. 342.3. That's going to be 0.219 moles. And then 200 grams of water. Water has a density of about 1 gram per milliliter. So this is 200.0 milliliters, or in other words, 0.2000 liters. So you'll notice we've got a little bit more than a 1 molar concentration solution here. And in the end we'll get pi is equal to 0.219 moles times 0.08206 liters atmospheres per mole Kelvin. 25 degrees Celsius is going to be 298 Kelvin. And we have 0.200 liters. So what is the pressure going to be? 0.2191 times 0.08206 times 298 divided by 0.2. And you see it's 26.8 atmospheres. 26.8 atmospheres is our final answer here, which is a really high pressure. Now that doesn't mean that your sugar water is going to fly out of the cup with the force of 26.8 atmospheres. But what it does mean is that if you wanted to put a selectively permeable membrane and press down on it to generate pure water through reverse osmosis, then you would need to apply a pressure of 26.8 atmospheres in order to accomplish that. Or if you put your sugar water solution in contact with pure water through a selectively permeable membrane, then the water would flow through that membrane in order to dilute the sugar water until there was a difference in the water levels that added up to a hydrostatic pressure of 26.8 atmospheres. This is actually really important for from a civil engineering perspective. You can find videos of how soil or parts of structures becoming waterlogged can actually exert incredible forces to damage or ruin a building or structure because just a little bit of water, when it is acting through osmosis, can exert a tremendous amount of pressure and cause lots of damage. So anyway, and again, we'll actually revisit osmosis with the quiz, so I think we'll leave it at that for now.